We will go over the debug in this lecture. The first step is to configure strong swan to debug the IPsec process. This is done using the command sudo ipsec log level any with number 4 giving us full details. We will also tail the syslog file and redirect the output to a file called IKEv1. This way we can scroll through the file and get the details of the debug. Now we will bring up the IPsec connection. The connection is up and established successfully. To get the detailed debug, we will now open the log file. There is a lot of information in the file, and there are information repeated in the debug output. This is because multiple processes record their IPsec events. This event indicates that the IPsec connection was initiated for the connection of Sun-Moon. The system checks to see if an IKEv security association exists with this name. There isn't any, which would trigger the connection. Here the kernel is identifying which interface to use for the connection. This is indicated by the kernel get root logs here. The IPsec process has to first create a security association. This message indicates the creation of one. The IKEv process is crafting the packets. It will need to create the attributes which include the vendor ID payloads, the IS camp negotiation parameters. Also, we see here it is preparing the certificate information. It is also preparing for the quick mode. This means it's identifying the left and right subnet or network A and network B. We recall from the previous lecture that each side put together the vendor IDs that it supports. Here the IKEv process is appending those fields in the queue to be sent to the remote peer. It is also checking the proposal to build the transform set information, meaning which encryption, hashing, and Diffie-Hellman group it supports. It is putting together the header of the packet that will get sent. Here we see the inner workings of the process. The system is calculating all the different bits and payload length to put in the header. This indicates that the transform set or the proposals is getting prepared. Finally, it is sending the first main mode message 1 to the peer. Here we see this side will basically start a 4 seconds timer for the return of main mode message 2. If not received within that time frame, this will make this side abandon the connection. Thankfully, it didn't wait for long. We see here that it received a response. It is parsing the response. Now it has the security parameter index that was set by the remote peer. It finished parsing the header. We see now that the two SPIs are recorded. It is parsing the proposal sent by the responder. It is also parsing the vendor IDs from the responder. Going through the debug is boring, however, it shows us exactly what happens. Here we see each vendor ID is getting parsed by the system. We see now after message 2 was received, the initiator gets the list of proposals the other side supports. This would result in selecting the proposal that matches. Here now the initiator knows the Diffie-Hellman key size to use. It will be generating a Diffie-Hellman key size of 767 bits. We see similar messages from multiple processes. Each process record the action it took, which results in repeated information. However, it's from different processes. Here we see the char on process parsing the NAT discovery message. Message 3 includes sending the Diffie-Hellman key and the nonce for the initiator. We see here this side is generating the nonce. So, all those messages go over the process of crafting message 3, which includes building the header, appending the Diffie-Hellman key, and the nonce for the initiator. Now that the headers and payloads are constructed, the char-on process hands the information to the IPsec process. The IPsec process determines what, if any, encryption needs to be done before sending the packet. Message 3 is not encrypted, however. Finally, message 3 is sent. A timer is started which would wait 4 seconds for message 4 to be received from the responder. Message 4 is received. It is 235 bytes in size. As we discussed in the previous lectures, the SPIs are used to match the session and determine for which IKE security association this message belongs to. There could be hundreds of tunnels. The SPIs allows the matching to the correct process. Now it is parsing the Diffie-Hellman key generated by the responder. It is also parsing the nonce generated by the responder. As you know, all information are now received. This side can now calculate SKIDA, DNE. Here also we see the matching of the SA message based on the SPIs. We see here that after parsing the request, this side determines that the responder is requesting a certificate issued by the strong swan CA. This is another message listing exactly the order of fields in the payload. The first field is the Diffie-Hellman key, the second field is the nonce, the third field is the certificate request. Finally, the last two fields are for the NAT discovery messages. Based on the Diffie-Hellman key received and the nonce as well as the other information, the Diffie-Hellman shared secret is calculated. Here we see that the system is generating the SKID and the encryption, authentication and phase 2 quick mode keys. Now it's crafting the fields for message 5, which includes the initiator requesting a certificate from the responder, a certificate that is issued from the strong swan CA. Part of the information in the certificate request is the initiator providing the public key of the certificate, which is listed in the ipsec.conf file for this connection. This is the certificate that is issued by the same CA. As you see here, this is the cert with the common name of sun.ca. Now it is generating the fields as well as the signature. The signature is the hash of initiator, encrypted and hashed using the private key of the certificate. This is the certificate that we just talked about with the common name of sun.ca. So, it is sending the ID field followed by its own certificate, followed by the signature. Finally, the certificate request for the responder. I will scroll quickly here until we get to see new information. The debug goes over every step of the way, including crafting the header, encrypting the payload, generating the hashes and signature. Once all those steps are done, it will send message 5. Finally, here is message 5 getting sent. And we see that it will be waiting for 3 seconds for the message 6 to be received. So, here it is receiving message 6 and parsing the payload. Anytime an IKEv1 packet is received, the SPIs are checked to see which IKEv1 session this packet belongs to. It is parsing the encrypted data. Remember that message 6 is encrypted by SKIDA and hashed by SKIDA. It is decrypting the payload now to extract the information. Now it has the plain data decrypted. As it is receiving message 6, the responder sends its own certificate that is issued by the same CA. It is parsing the signature, which is the hash of responder encrypted by ASCII IDA and hashed by ASCII IDA. This here shows that the parsed data includes the responder ID, the responder cert and the signature. The debug shows the cert details. Certificates are also called X5 or 9. With a full debug you have duplicate information unfortunately. However, here we see the certificate and its serial number information. It is issued by the Strong Swan CA. The subject common name is moon.ca. Here in a clear way the debug shows us that the certificate received is with this endpoint entity common name. Now after it decrypted the content, it has the hash for the responder. It will run the same calculation and match the calculated hash with the received hash. If they match, then the peer is validated. Here we see it is checking the CA to see if it has a certificate revocation information. There isn't any configured for this CA. Usually, if you have a CA, it has a certificate revocation URL that can be checked to validate certificate status. The last line here shows that the certificate authenticated successfully. That means both hashes match. It will then schedule reauthentication after the IKEv lifetime expires. Quick Mode Phase 2 can now start. Quick Mode Phase 2 process is now activating. It is checking what proposal exists for this peer. We limited it to a single transform of ASP with triple DES, MD5 and there is no PFS. It is doing the steps for phase 2, which includes identifying network A and network B, which are shown in the debug here. It is generating the quick mode message. Now if we issue the IPsec status, we see an established tunnel. During phase 5 process hash I is calculated. Hash initiator is what gets hashed and encrypted, which means getting signed. We didn't actually catch the hash I, but if we grep for it in the log file we will find it. Hopefully going over this debug was useful to you. We will talk more in the next lecture.